Welcome to the Problem Channel Season 2, Episode 49, the episode which I titled Modular Equilateral Chameleons, because in this episode we will solve a beautiful mathematical problem that deals with color transitions among the members of a family of chameleons. But before we deep dive into the underlying mathematics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to derive the maximal academic benefit from working with the material presented on this channel is to go to the homepage of this channel and in the channel's trailer section, find the episode The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E49, we are told that once upon a time there lived a family of chameleons on a tree, and each and every chameleon in that family could be only one and only one solid color. For example, each and every chameleon in that family can be solid red and no other color, or it could be a solid green and no other color, or each and every chameleon in that family could be completely solid blue color and no other. And in that family, during the daily interactions of the chameleons of that as a members of the family on the tree, the following color changing interactions can happen. If any two chameleons of the same color meet, then no color transformation happens across these two members of the family of chameleons. In other words, if two red chameleons bump into each other, then they both stay red. If two green chameleons bump into each other, then they both stay green, no color transformation happens. And if two blue chameleons run into each other, then they both stay blue and no color transformation takes place. However, if any two chameleons of distinct colors meet, then both of these chameleons turn the remaining color pretty much instantly or very, very fast. I captured that fact in the table shown over here in the center and on your right, and that means the following. If one red and one green chameleon bump into each other, then they both become the remaining color, which is what? Blue. If one red and one blue chameleon bump into each other during their daily routine, then they both turn pretty much instantly or very, very quickly into the remaining color, or they both become green. Lastly, if one green and one blue chameleon bump into each other during the daily routine, then they both pretty much simultaneously, instantly or very, very quickly turn the remaining color, which is red. And here, why the stipulation before that if any two chameleons of the same color meet, then no color transformation happens is important, because after the color transformation in each case, when two chameleons of distinct colors meet, shown there, here, and here, depicted at the bottom here, here, and here, then technically the two chameleons are still in close proximity to each other. They still are in the bump into each other state, but because they now have the same color, no further color transformations happen. This is an important detail, and that makes the overall logical content of this problem cohesive and correct. The question in this problem is the following. Can it so happen that all the chameleons in that family will turn one and the same color, which one doesn't really matter, in a finite number or in the finite amount of time, if we assume, for example, that the chameleons begin bumping into each other, let's say every second again, or every hour, it doesn't really matter. If initially, and this is where the crux of the matter comes in, if initially there were 27 red, 25 green, and 27 3 blue chameleons. Like many problems on this channel, this particular problem is open-ended, and the viewers of our channel who tag along by now know all too well that a technical problem is open-ended if the exact or precise scenario that will unfold in the given problem is not specified in the statement of the problem. And in this particular case, as is evident, the question is, can it so happen? That means that the burden of deciding which way the scenario in a given problem will go or will unfold is precisely on us, the problem solvers, and this is precisely how all hard sciences, mathematics, theoretical physics, and computer science work. And in a sense, it can be said that in all these hard sciences, the essence of the work that people do in these sciences is precisely dealing with open-ended problems or with open-ended situations where we do not know yet, but then eventually we do find out. As such, if we think that the answer to the question posed is in the positive, then the burden of producing at least one legal algorithm or one correct sequence of color changing meets that shows that yes, here's how all 27 plus 25 is what? 52, and 23 is 75. Here is how all 75 chameleons in this family, by following this specific sequence of color changing meets, 1, 2, 3, become all red, or become all green, or become all blue. That burden of producing such a legal and correct algorithm or color changing meets sequence is on us. But if, on the other hand, we think that the answer to the question posed is in the negative, then the burden of showing correctly that no matter how initially 27 red, 23, 25 green, and 23 blue chameleons interact with each other, no matter how they do that, they will never turn one color. All 75 chameleons will never become one and the same color in a finite amount of time. Now, to the newcomers to mathematics in general and problem solving in particular, this problem may seem absolutely strange and absolutely weird. It doesn't really seem at first blush that it is even possible to solve this problem, but again, the viewers of our channel who tag along know that this problem may be solved using the so-called invariant problem solving approach. And in the lightning round, the way this approach works is as follows. If we think that the invariant problem solving approach may help us generate a solution of this or that technical problem, then we should try to partition all the material in the given problem into two distinct piles. Into one pile, we will put all the material that does vary, and into another pile, usually quite smaller than the first one, we put all the material in this given problem that does not vary. Each and every unit or each and every quantity that does not vary that we uncovered in this analysis we refer to as an invariant. And then, even though by now we know that problem-solving approaches are heuristic templates that do not really provide any algorithmic guidance, but then according to the invariant problem-solving approach, we have to shuffle through the pile of invariants and see which one invariant maybe or which combination of invariants will provide us with a tactical advantage and will allow us to generate a solution of the problem at hand. By now, we solved several problems using the invariant problem-solving approach, and we know that not all invariants are created equal, in the sense that if we think that the answer to the question posed is in the negative, and it is, we have good reasons to suspect, our hunch, our nose is telling us that we do not think that it is possible to produce the requested configuration, then a useful invariant that we may uncover in our analysis of the problem should be able to detect or discriminate against precisely these two states, the initial state and the requested state. In other words, an invariant that is useful for the generation of a solution of a technical problem at hand should be able to produce one value that corresponds to the initial configuration and a different value that is associated with the requested configuration. Precisely because these two values are distinct or different, that exact situation will tell us that the requested state is not reachable. As such, we will do precisely that. In this episode, we will apply the invariant problem-solving approach to the process of generating a correct answer to this here problem. And at first, we will look at the material that does change. In this problem, you do not really have to be an Einstein to realize right away that when, what was the initial condition? We had 27 red, we had 25 green, and we had 23 blue chameleons. In other words, in this problem, we do not need to be an Einstein in order to realize right away that every time that two chameleons of distinct colors change, two distinct colors meet, the distribution of the number of chameleons of this specific color will change every time, inevitably, no questions asked. For example, let us assume for a moment that initially we had 27 red, 25 green, and 23 blue chameleons, and it so happened that the very first meet was between one red and one green chameleon. Then what happened? Well, then the red, because these two colors are green, red is not green, green is not red, according to the rules stipulated in the statement of this problem, both of these chameleons turn the remaining color, the blue one. So after that meet, what will be the distribution? What will happen to the 27 red chameleons? Well, the 27 red chameleons will become 26 red chameleons, and 26 is precisely what? 27 minus 1. Now, what will happen to the distribution to the number of the green chameleons in this case? Well, the green chameleon in that family just became blue, so this number became 24, and 24 is equal to what? 25 minus 1. One less red chameleon, one less green chameleon, but these two chameleons are now what? They're now blue. So what happened to the population of the blue chameleons in this family? Well, it just grew by 2. So 23 was taken into 25, and 25 is represented which way? Is 23 plus 1 plus 1. Similar changes in the distribution of the number of specifically colored chameleons will happen every time any two chameleons of distinct colors meet. We can play around more with these numbers, but now that we understand that this is definitely what will vary every time two chameleons of distinct colors meet, next we want to look at the material in this problem that does not change. As we play around with different ways in which any two chameleons of this happy family of distinct colors meet and what that color changing means for the distribution of the number of chameleons of different colors mean and how does it work, we evidently again fairly quickly realize that one thing, one quantity that will definitely not change across all the color changing meets of the chameleons in this family will be what? The total size of the population of the chameleons. In other words, if initially we had 27 plus 25 is 52. 52 and 23 is 75. If initially we had 75 chameleons in this family in the initial state, then really no matter how any two chameleons of two distinct colors bump into each other and inflict the corresponding change that we just analyzed in the previous segment, the total number of such chameleons will remain one and the same. And how do we refer to a quantity that remains one and the same in a given context? We refer to that quantity as an invariant. Yes, the total size of the population of chameleons in this case will be an invariant in this problem. And again, for the nitpickers of the world, we can say that, okay, no new chameleons are born into this family and no existing chameleons die during this experiment. For example, we can say that this happy family is very active. The moment the sun comes up, they start doing their thing, bumping into each other, and two chameleons of distinct colors meet or bump into each other, let's say every second, and that happens many times during the day. So during that course of the day, we take it that the time frame during which we look at this experiment again is such that it is short enough for no existing chameleon to die and no new chameleons to be born. As such, we can symbolize things a little bit. So what can we say? We can say that, well, let's write it down over here. The number of red chameleons plus the number of green chameleons, RGB, plus the number of blue chameleons remains what? Remains constant at all times, which is one of our invariants. Is that the case? Yes, it is the case. In this case, that number is 75. Wonderful. That remains one and the same at all times. The number of chameleons before any color changing meet and the number of chameleons after any such color changing meet will be one and the same, which is captured over here. This is very good. And the next question is, what else remains invariant? Well, the very number of colors, red, green, and blue, also remains constant at all times. During our mathematical experiment, no new colors are added into the mix and no existing colors are removed from the mix. So the total number of colors, which is, let's say, we will write it down as the number of colors also remains what? Remains constant. And what do we refer to a quantity that remains constant in the given context of the problem? Yes, it is an invariant. Technically, yes, this is another invariant. But the question is, remember the remark that I keep making for several episodes now in a row. Not all invariants are created equal in the sense that not all invariants have the same usefulness weight, if you will, assigned to them. Now, fundamentally, are these invariants important? Well, the answer, of course, yes, they are hugely important. They are fundamentally important precisely because the number of chameleons in this family is taken to be constant at all times, and the number of colors into which these chameleons can transform or flip also remains constant at all times. We can construct our solution and we can build our analysis and construct eventually a solution. These two invariants, again, form a logical, if you will, foundation. They form a foundation on which we build the rest of our solution. Without these two invariants being in place, then we would need evidently to know the law according to which the number of the chameleons in the family varies, and a law according to which the number of colors varies. So this will perhaps make the problem even more difficult, but right now these two quantities are constants, these two quantities are invariants. But immediately, tactically, how do they help us solve the problem at hand, and how do they help us answer this open-ended question? Can this family turn all one color or cannot? Well, evidently, immediately, tactically, these invariants are not very helpful. And in the search for a helpful invariant, or again, one more time, an invariant that can produce two distinct values, one value associated with the initial configuration or with an initial state, and a distinct value that corresponds or is associated with the requested or the final state, if you will, that invariant that will be useful to us. And in a search for that invariant, we will do the next best thing that pretty much all mathematicians do when they run into a problem. We will experiment with small numbers first. The numbers in the Olympic style problems are usually cranked up so ridiculously high so as to basically to eliminate any possibility for a manual brute force solution, because the members of the jury of this Olympic contest, they are looking precisely for a creative or a clever solution, and in order to produce that solution we need to exhibit our creativity, ingenuity, and our improvisational skills. And the idea behind all these exercises is the following. When a person who is trying to generate such a clever solution for an Olympic style problem is trying to do that, then that person puts his or her mind into a state that is isomorphic in highbrow tongue, or basically essentially the same as the state of the mind in which a practicing mathematician finds him or herself in his or her professional capacity. So in other words, when a professional mathematician is trying to solve this or that technical problem, then the state of mind in which he or she operates is essentially the same as the state of mind into which we have to put ourselves in order to generate a clever, elegant, beautiful solution of a Olympic style mathematical problem, or problem in physics or in computer science. So because this number is so high initially, when we step into the problem, we do not really know what's going on. In the adrenaline rush and the excitement to solve this problem, we're in the fog of war. We do not really see what's going on. So here is one example that usually, or sometimes, I should say, sometimes is helpful, is the following. Construct a smallest, or the smallest in some sense, positive or negative example. In this case, by looking at the statement of this problem, it becomes very, very straightforward to generate a smallest positive example when we can cook up an initial population of chameleons that can be taken into the requested state. All chameleons become one color in the finite amount of time, actually in 1 unit of time. And what is such an initial configuration? Well, if we have one red, if we have one green, and if we have one blue chameleon, 1, 1, 1, perfectly fine and valid initial configuration. The total size of this population is 3. Then in one step, in 1 unit of time, in 1 second, for example, any meet between the members of this smallest successful story family will produce what? Will produce the requested state. For example, if we have one red plus, let me carefully write this down, plus one green, this will result in what? This will result in blue, blue, blue. So we'll have blue, 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 3 chameleons of one and the same color, blue. If we have one red and one blue chameleon bumping into each other, what will we have? Well, we will have these two guys will become green, this green and this green, and the green that was initially, and voila, we have a solution. All 3 chameleons in this family become green in a finite amount of time. And if we have what? A green and the blue chameleons bump into each other, hello, hello, how is it going? Bam, bam. Red, red, and initially red. So we'll have red, red, red. All 3 red. Solution is at hand in 1 unit of time, which is a perfectly finite number. Here is a valid sequence how this entire family can become one and the same color. Wonderful, we can already start playing with things. Okay, so what is the secret sauce that ensured a successful story behind the color changing transformation in this family? Well, we can start playing already, we know, with simple. Does it in some sense? What are the simple constructs? Well, sums, differences, products, and ratios usually come to mind. We don't need to be get too involved, but for example, we see the sum 1 plus 1 plus 1 is 3. So 3, the number of colors is the same, 3. So here some people will say, okay, 3 modulo 3 is 0 in one case, 3, 3. Here the sum is 1 plus 1 is 2, 2 modulo 3 is 2, so 2 is not 0, so the sum probably will not work. How about the difference? So we start playing around with things, and again, in real time, different people will luckily approach the solution, the problem in different ways. We encourage our viewers to share their ways, how they came up with a solution of this problem, but here we will look to a next smallest and simplest successful story when in this case the numbers were all odd, and in the next case, why not, we will try to look at the smallest example where all the numbers initially are even. Here, some of our viewers may say, Roman, why are you taking the next example to be 2, 2, 2? Well, the answer is just because we worked with odd numbers, all odd numbers. Let's try work with all even numbers, because why not? We do not know what to expect, and what we do when we deal with an open-ended problem is we're trying to bite off only as much as we can chew and swallow. In other words, we're trying to deal with something that we can understand currently, and then working with that currently understandable material. Sometimes it so happened that, so to speak, the solution vector, bam, pops out, and we say, oh, that's the way to go, and we chase that hunch and that idea to the finishing line, and hopefully um, we have something to write home about the success story. So here, let's say we have two red, two red, two green initially, and we have two blue chameleons initially. Ready, set, go, bam, the clock is ticking every second. Something happens over here. In this case, already we have more material to play with. We can have two red chameleons bump into each other. We can have two green chameleons bump into each other. We can have two blue chameleons bump into each other. Nothing interesting happens, but okay, let's say we put this aside. Only interesting needs happen. What do we see? Well, we see that essentially we have our previous experiment multiplied by 2, so to speak. We double the size of the family precisely that way, and we already see, okay, in the first, what is a valid, legal, and correct sequence of color changing meats that will put all the members of this family into one and the same color? Well, it's similar to this one. For example, let's say we have one red and one green chameleon bump into each other, so the number of red chameleons becomes 1, the number of green chameleons becomes 1, the number of blue chameleons becomes what? 4, correct. And what happens next? Well, these two guys bump into each other, and then this becomes big fat 0, this becomes big fat 0, and what does this become? This becomes 6. With those members of our audience who have the physicist inside them, what can we say here? Well, the law of conservation of the number of chameleons in the family is 6. 2 plus 2 plus 2 is 6 initially, 6 finally, 0, 0, 6. Everything is good. We haven't lost anyone. We haven't gained any new members, but all 6 chameleons in this case are one and the same color, blue. Likewise, we can make on demand. If you want us to flip all the members of this family into red, we can do that. Don't be shy, do that. Or we can flip all the members of this family into green. do that. I will not do that, but you guys should do it and prove to yourself that this is possible. And what do we see in some sense? Well, algorithmically or tactically, what is the strategy? Well, we understand that 2 and 2, for example, here we work with these two chameleons of these two colors, red and green, but you can work with the chameleons of any other two colors in the same way. The result will be the same. Strategically, what's the winning strategy in this case? Well, if we can somehow make the number of red and let's say chameleons and the number of green chameleons one and the same, it doesn't really matter. 3 and 3, 4 and 4, 5 and 5, 17 and 17, 59 and 59, 1001 and 1001. It doesn't matter. As long as they are the same, that's it. Game over. We won. Because what do? We keep for a legal, valid, and correct algorithm. What do? We keep bumping these two guys into each other, reduce this by 1, reduce this by 1, increase the remaining, the number of the chameleons of the remaining color by 2, and boom, 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 whittle down these numbers to 0 and put all the members of this happy family into the remaining color. The question is, however, how or when can this situation be achieved and produced? So now we play with some more numbers, we develop some hunches, and then we realize that essentially this problem is actually not about the chameleons bumping into each other and changing their colors, but according to the reinterpret and conquer problem solving approach that we already studied prior, this problem is what? Is about what? This problem is about ordered triplets of numbers. And again, my ordering of these numbers in the triplet RGB is arbitrary just because I decided to do so. Any other ordering will work, but fundamentally or essentially, the first step towards a winning approach, a winning strategy, is to realize that again, this problem is not about chameleons changing their colors in the color changing meets, but this problem is about ordered triplets. As such, from the ordered triplets of whole numbers perspective, as we begin fishing for a useful invariant or an invariant that can discriminate between the initial state or an initial configuration and the requested or the final state or final configuration, we play games with what? With popular operations. There is no really transcribed law in mathematics which says, oh, when you see this, try that. There is no such thing. We try, we fail, we try again, we fail, we'll try again, maybe we succeed. And in that process, we develop the intellectual stamina or the resistance to failures and willingness to not give up and keep fighting. So here, let's try the sums, for example. In the initial state, 1 plus 1 is 2. 2 modulo 3 is 2. In the final state, for example, there will be 0 is 0. 0 plus 0 is 0. 0 modulo 3 is 0. And 0 is not 2, but the story is successful. We did produce something that we do not even know if it's invariant or not. We're just playing, but we produce something that discriminates between two states, the initial and the final, but it sits on top of a success story. We did manage to produce a family of chameleons that are of one and the same color. So the sum probably will not work. Likewise over here, 2 plus 2 is 4, 4 modulo 3 is 1 in the initial state, and the final state is 0, 0 is not 1, 1 is not 0. So we do have something. We do not know if it's an invariant or not. This is just a guess. But it is something. This is a candidate that produced two different values, but this is a success story, so that doesn't really help. Okay, so the sum of elements. So why, for example, you guys can also say, Roman, why did you pick these two guys? Well, just because. You can pick these two or these two, it doesn't really matter. For me, the easiest first two numbers I see, why not? Now, so the sum we eliminated, let's put it this way, the sum of numbers we eliminated. And also another valid question is, Roman, it looks like you pulling a magic rabbit out of a hat. Where did this modular 3 came from? Well, remember we have three colors. We discussed this. We have a fixed number of colors. The number of colors in this problem is an invariant. Whenever we deal with whole numbers where the width in some sorts of our data set is fixed, it is a good idea to try to see what will happen in the modular arithmetic sense when the actual values don't really matter for the entire possibility, for the entire universe of numbers, but only on a particular short and small line segment of these numbers. So now we try the next hunch. Okay, let's see what happens with the difference when we treat our problem as basically dealing with sets of ordered triplets of whole numbers, and by now we understand at least two of these numbers must be positive. Think about it. Think about why. So let's say 1 minus 1 in the initial state is what? Is 0. 0 modular 3 is 0. That's the initial state. In the final state, let's say over here we have all chameleons are blue, so these two numbers are 0 again. 0 minus 0 is 0. 0 modular 3 is 0. And 0 in the initial state, 0 in the final state. Seems to work. We did produce a success story, and we did produce a magnitude that we do not know if it's an invariant or not. This is our hunch. We're just experimenting with things. And okay, this experiment seems to work. We play with other color distributions. It works. Try it. And with our last experiment over here, 2 minus 2 is what? 0. 0 modulo 3 is 0. That's the initial state. So we will write the candidate invariant initially is 0. And in the final state, let's say in this example, 0 minus 0 is 0. 0 modulo 3 is 0. 0. And the candidate invariant, how many steps did it take? This is a success story of length what? Of length of 2. Finite number, 2 units of time, or 2 steps, 2 color changing meets. So in 2, we also produce 0. 0 is equal to 0. This is a success story. So now we get a hunch. Maybe there is some mathematical heft. Maybe there is some mathematical substance behind the idea of taking the difference between the elements of the ordered triplets. And now we take that idea further. Using the reinterpret and conquer problem-solving approach, we realize that algebraically this problem may not be as much as about chameleons changing colors, but about manipulation of ordered triplets of whole numbers. I emphasize the word algebraic because in a few minutes we will see that this problem has an absolutely wonderful, absolutely awesome geometric interpretation. But before we get to the geometry of the chameleons changing names, we will work with the first word in the title of this episode, modular equilateral chameleons. Equilateral evidently is a hint that there is an absolutely beautiful geometry hiding behind this problem. We'll get to that in a minute. But working with the modular is algebra. So an algebraic essence of this problem is what? Let's say initially at some time the sun came up, the family woke up, they started going about their business, they started bumping into each other, color changing meets. At some point of time, we train our telescope or microscope, if you will, onto the family. Bam! We see R0 red, G0 green, and B0 blue chameleons in that family after the last color changing meet. And then no matter how, that's the idea from the algebraic standpoint, the analysis is complete. No matter how these chameleons bump into each other, the next time the color changing meet takes place, what can happen? Well, the first thing can happen is this. The red and the green chameleons meet, and that means the original ordered triplet RGB is taken into what triplet? R minus 1, G minus 1, B plus 2, because now there are 2 more blue chameleons in this family. because they came from these two, from one from green, one from green, one from red family. If one red chameleon and one blue chameleon bump into each other, then the original triplet is taken into what? R minus 1, B minus 1, G plus 2. Number of green chameleons is now 2. Lastly, the only one valid and legal situation is what? One green chameleon bumped into one blue chameleon. These guys became red, and the number of red chameleons is now plus 2, R0 sub 2. This description is complete. There are no other scenarios. So now that we have that on the books, the question is, this is transition right here, how do we convert our hunch or our hunches that we develop by playing with sums, differences, modulo 3, modulo whatever, how do we convert these loose hunches into a solid mathematical proof? We convert our hunches into a solid proof by doing basically a very straightforward, almost kindergarten level variety case-by-case analysis. In other words, if in the first case one red and one green chameleons bump into each other, we have this transformation captured algebraically over here. So what is the difference between the number of red and the number of green chameleons after that transformation? We'll write this as R minus G is equal to what? R0 minus 1 minus G0 minus negative 1 plus 1, negative 1 and positive 1 cancel each other out. So we see in this case the delta, let's write it down here, delta is equal to 0. Next, we construct the difference between the number of the red chameleons and the blue chameleons after that particular meet. What will it be? Red minus blue is equal to R sub 0 minus 1 minus B sub 0 minus 2 minus 1, and minus 2 is what? Minus 3. So this will be minus B sub 0. We can even put it in parentheses like this, just to be perfectly clear what's going on. Minus 3. So in this case, the delta is equal to negative 3. Negative 3. And the last case, when we construct the difference between the number of green and the blue, green and blue chameleons after the transformation, this will be what? G sub 0 minus 1, basically the same thing, minus B sub 0 minus 2, minus 1 minus 2, negative 3. So G sub 0 minus B sub 0, again, our initial difference, negative 3, and the delta in this case is also negative 3. So the conclusion that we draw that under this scenario, the difference between the number of chameleons of each color, taken in that order, the number of red chameleons minus the number of green chameleons, the number of red chameleons minus number of the blue chameleons, and the number of green chameleons minus the number of blue chameleons is what? Either does not change at all or changes precisely by negative 3. And that completes the analysis of the first case. Wonderful. Now we analyze the middle case in exactly the same fashion. The difference between the new number of red and green chameleons, just in the same fashion, will be what? The number of the red chameleons in the initial state minus the number of the green chameleons in the initial state. Negative 1 minus 2 will be negative 3. So the delta over here will be negative 3. We will record it carefully over here. Again, the number of red chameleons minus number of blue chameleons will be what? R 0 minus 1 minus b sub 0 minus minus 1. Minus 1 and plus 1 cancel each other out, so this will be minus b0. In this case, delta is equal to 0. The difference between the number of red and blue chameleons before they meet and after the color changing meet is exactly the same. And lastly, we construct the difference between the number of green and blue chameleons. In this case, this will be g sub 0 minus b sub 0 will be what? Plus 2 minus negative 1 plus 1. 2 plus 1 is 3, so this will be plus 3. So here in this case, delta is equal to positive 3. Positive 3, and that scenario over here completes the analysis of the middle case. Wonderful. We now carry out the analysis of the last case, the difference between the number of red and green chameleons in this case will be what? R0 plus 2 minus G0 minus negative 1 plus 1. 2 plus 1 is 3, so this will be minus number of green chameleons originally plus 3, so we record officially the delta is equal to plus 3. That arithmetic over here is nothing very complicated at all. The difference between the number of the red and the blue chameleons after this color changing meet will be what? R sub 0 plus 2 minus b sub 0 minus negative 1. 2 plus 1 is 3, so minus the number of blue chameleons originally. If we put the parentheses here, that will be plus 3 again. So the delta over here is plus 3. And the last case, the difference between the number of green and blue chameleons, will be what? G sub 0 minus 1 minus b sub 0 minus negative 1. Negative 1 times negative 1 is plus 1. Minus 1 plus 1 cancel each other out. So here there is no change as to be expected. Delta equals to 0. And look at this. After this straightforward analysis, we proved algebraically, beyond any reasonable doubt, that under any legal color changing meet between any two distinctly colored chameleons in this family, the change between the correspondingly computed number of chameleons of each color over here changes what? Changes how? It either does not change at all, like for example here, here, and over here, or it changes precisely by minus 3 or plus 3 as shown over here. And whenever we deal with integral quantity or whenever we deal with whole numbers, and these whole numbers change in this very carefully orchestrated way, something initially, then something later, plus minus n, then we already know that the whole thing modulo n is a perfect candidate for a useful invariant. Observe that which particular difference across the three differences that we analyze we pick for an invariant does not matter, because all such differences behave in exactly the same favorable to us way. These differences either do not change at all, as shown over here, delta equals 0, delta equals 0, delta equals 0, or these changes vary in such a way that they change across one colorful transformation by negative 3 as shown over here, or over here, or over here, or such different changes by precisely positive 3 as shown over here, and over here. Again, which difference you pick for delivering the or walking the last mile and generating a solution doesn't really matter. Let's say I pick this one, r minus g. So let's look at this difference over here. means what? If we divide these two numbers, integer divided by 3, they will evidently generate one and the same residue. They are equal, so the residue will be 0. These two numbers over here are technically different. The difference between them is -3, but again, upon the integer division by 3, this -3 is divisible by 3, contributes nothing to the operation of integer division by 3, it vanishes. And likewise, the +3, the +3 in this case, technically r minus g and r0 minus g0 are different numbers, but they differ precisely by 3 by our modulus. So upon integer division by 3, this +3 vanishes, and the difference r minus g, the difference between the number of the red and the green chameleons after each and every colorful transformation upon the integer division by 3 generates one and the same number and remains an invariant. And what does that mean? Well, that means at least two things. One, that we fundamentally solve the problem, but another interesting observation that we can make over here is the following. If we pick, for example, this difference as our invariant, then it looks like all the other invariants will follow automatically. And how can we show that? Well, let's take a look at the difference first between the number of the green and the number of the blue. Let's see if I can erase this fairly well so you guys don't have to watch me doing all this erasing. Let's see. The difference between the green and the number of the green and the number of the blue chameleons, we expressed, for example, in, let's say, in this way. What was it? It was G0 minus B0 and what else? -3. But let us massage this difference over here in terms. The idea is that we want to express these differences as a function of our invariant r minus g modulo 3, and we know that all these three numbers and across all the possible distributions are locked into what relationship? R plus G plus B is equal to S, and S is our other invariant. So here we want to slide in or introduce this difference. So we add R0, then we subtract G0 like so. Then we have to subtract R0 to balance things out. We subtracted G0, so we need to add G0 over here. Then we had our original G0, so we need to have plus G0. We had negative B0, negative B0, and what else did we have? We had -3. Now let us keep working with this material like so. So we have this guy, so negative R0 and negative B0, how can be manipulated? R0 minus G0 minus R0 plus B0. What else? Plus 2G0 minus 3. But now you already see what's coming. What is this? R0 plus B0. What is this? Well, by the virtue of one of our invariants, this will be what? This will be S minus G0, because R0 plus B0 plus G0 is S. So this sum is S. The sum of these three numbers, this is our invariant, R plus G plus B minus G0. Slug it in into this relation. What do we have? R0 minus G0 minus S plus G0 plus 3G0. So minus S plus 3G0 minus 3, and voila, look at this. Upon the integer division by 3 of this difference, what do I have? -3 vanishes. 3 multiplicative copies of G0 vanishes. S is an invariant. No matter how we slice and dice our colorful transformations, this number remains the same. the residue that it will generate upon the integer division by 3 will remain one and the same. This number over here will generate, this is our invariant. Remember, we locked it in as our invariant. Upon the integer division by 3, this number does not change. Voila, we just proved that if our difference r minus g mod 3 is an invariant, then g minus b modulo 3 will also automatically be an invariant. So this takes care of the difference g minus b. And let me do it fairly expediently here. At the bottom, guys, erase all this. Pause the video and rewind if you have to. It's not complicated. So now we did g minus b. So what's left? R minus b. So r minus b was r0 minus b0 minus 3 in the first case. I mean, the other cases are analyzed in exactly the same way. The essence remains the same. We always have 0 or plus 3 minus 3. So upon integer division by 3, all this pesky plus minus 3 vanishes, so things work out. What do we do here? Well, we introduce our difference, so it will be r0 minus g0. You see, we artificially introduce negative g0. But then to balance things out, we need to introduce with a positive copy, plus g0. This is 0, right? And minus b0, and in this case minus 3. But we just showed what? Upon integer division by 3, this number will be 1 and the same. Negative 3 plus 3 or 0 doesn't really matter, covers all three cases, will vanish, will not affect the result. So integer division by 3, the residue that this number will generate upon the integer division by 3 is what? Also will remain invariant, invariant, invariant. So if we pick one invariant, all the other invariants follow automatically. They pop out of the machinery of this situation, of this problem, automatically. And that means, again, that we can pick any such difference. Let's write it down officially. Invariant equals r minus g mod 3 is our invariant. And what do we do now? We apply our invariant to two distinct states, the initial state and the requested state. In the initial state, the value invariant, let's designate it with 0, is what? 27 minus 25 mod 3 comes out to what? 27 minus 25, 2. 2 mod 3 is 2. And in the requested state, invariant in time less than infinity, some number, what will be the case? Well, in the first case, we have to analyze what? Let's say all the chameleons become red somehow magically. So that number will be, let's do over here, 75 mod 3 is 0. 0 is not 2, 2 is not 0. That already proves that with these specific numbers, 27 red, 25 green, 23 blue chameleons, this happy family will always be, there will be some members of this family that are of different color. This family can never be painted into one and the same color in any finite number of color changing means. Let's say somehow magically all the chameleons became green. Then the difference will be what? 0 minus 75, negative 75, negative 75. But that's the same thing, doesn't really matter. 0 is the answer again. 0 is not 2, 2 is not 0, again, impossible. And if all chameleons somehow become blue, this becomes 0. 0 minus 0 is 0. 0 modulo 3 is 0 again. So in all three cases, this is not happening. So this is the answer to the question posed specifically with the numbers that were given, 27, 25, 23 for the RGB. You can cook up the other numbers. And the answer to this problem, again, in the way it was posed, is in the negative. No, in no finite amount of time, this happy family of chameleons can be painted into one and the same color through the legal and valid color transforming meets between the members of this family. Now we covered the modular, the word modular in the title of this video. This takes care of the algebra. But next we will move on to the word equilateral in the name of this, in the name of the title of this episode. We'll understand where did the word equilateral came in, and it turns out that this specific problem has also an absolutely beautiful geometric interpretation. And as I mentioned many times in the past, and I'm sure I will do so many times in the future, a beautiful mathematical idea is pretty much indistinguishable, or essentially is the same as a beautiful work of art. As for example, this painting, please take a look. As a friendly challenge, see if you can at least figure out to the brush of which famous painter does this watercolor belong to. But again, if we examine that work of art, we will see that the balance between the light and the shadows, the balance between the different positions of the objects that we saw in this painting is just so perfect. No specific detail pops out, no specific detail is sunk in or lost in the woodwork. Everything is just perfectly so, and that exactly will be the case with the upcoming geometric interpretation of this problem. There are at least three pedagogical reasons why I want to share the upcoming beautiful geometric interpretation of this problem with you. The first such reason is the fact that the algebra and the geometry in any situation are mutually beneficial. In other words, here I'll get a little ballsy and go against the opinion of some mathematicians, granted people with PhD titles in mathematics who try to avoid geometry at all costs. I still think that algebra and geometry in general enjoy a mutually beneficial relationship, and the algebra of the underlying problem enriches and deepens our understanding of the underlying geometric interpretation of that algebra, and conversely, the geometry of the underlying problem may help us generate new ideas that deal precisely with algebra, which means that ideally, of course, and on this channel, I do not really have that much time all the time to do it all the time, but ideally, every time we solve a problem that seems to be algebraic, we should try to look for a geometric interpretation of the problem, and conversely, every time we solve a problem in geometry, we should try to construct a bridge back into the land of algebra. And these two seemingly different, let's say, layers of mathematical study, they actually enrich each other and flip-flop with respect to each other with good ideas. That is reason number one. Here, for example, even in the disciplines that seem to be very abstract, such as the theory of groups, I still think that the algebra and the geometry of any situation enjoy a mutually beneficial and symbiotic relationship. In my free book, Group Theory for All, an elementary introduction to the theory of groups, I try to show just that. And if you read this book, you will see that on the one hand, for example, a multiplication table of a group, yes, it gets quite horrible quite fast. It's not scalable, but it's one way to look at the geometry of the group, where the group operation is the king. It shows the way in which all the elements in the group interact with each other. It gives a complete description, and that is why it gets very unscalable very fast. On the other hand, the other object called a graph of a group is quite scalable, and it also gets us or allows us to understand the algebra of the group in a different way, and hopefully deepens our understanding of the structure of the group. The second reason why I want to show this geometric interpretation of this problem with you guys is to showcase the idea that elementary is not easy. Quite the opposite is true. There quite a bit. There are a lot of problems that are deemed to be elementary, but that are quite difficult. And the proof of that statement, if you guys do not agree, then the question is, why didn't you come up with this geometric interpretation of this problem on your own? You see, this is precisely the point. If something is elementary, it does not mean that it is easy. And the third point, the third reason why I want to share the a geometric interpretation of this problem with you is to show that befitting exactly the problem-solving approach that we're studying right now, the invariant, my claim is that creativity, ingenuity, and improvisational skills in mathematics, theoretical physics, and computer science, they remain invariant. They remain invariant under what? Under the operation of change of the underlying material to which creativity, ingenuity, and improvisation are applied. And that means that the texture and the quality of creativity, ingenuity, and improvisation that is applied to, let's say, kindergarten primitive material of points, line segments, and triangles actually remains the same as the creativity, ingenuity, and improvisation that is applied to non-elementary material. When we apply the creativity, ingenuity, and improvisation to analytic continuation, analytic extensions, field continuations, quadratic residues, nonlinear differential equations and partial derivatives, residues of holomorphic functions, and on and on and on. The texture and the quality of the creativity, ingenuity, and improvisation with which we manipulate highbrow mathematical objects remains exactly the same as in the case when we apply creativity, ingenuity, and improvisation to the kindergarten primitive material, points, line segments, triangles, angles, and so on. And that means, in some sense, maybe that is not what you want to hear, but this is why we do this. We use the primitive, the kindergarten level material as a dress rehearsal for the application and for the developing the knack to be creative, show ingenuity and improvisational skills when we manipulate mathematics. And again, the sad statement here is that if you cannot exhibit creativity, ingenuity, and improvisation when it comes to the primitive, the kindergarten, the basic elementary material, then what reasons do you have to think that you will be able to do the same with the highbrow or grown-up mathematics? There are no such reasons, so try to do that every time you solve a problem that has the algebraic flavor. Try to step into geometry, 2-space, 3-space, maybe it's Euclidean, maybe it's not Euclidean, maybe it's hyperbolic geometry, maybe in a different type of geometry you can find a different implementation. And conversely, every time you solve a problem that's geometric in nature, jump back to algebra and see if you can dig out something interesting here. Coming back to the idea and covering the equilateral in the name of our in the title of this episode. Remember that season 2 math problem 30, those of our viewers who tag along remember, we covered the problem in season 2 episode 28. Season 2 episode 28 over here. If you guys missed it, you may want to go back. I think the title of that episode was, is it a hexagon or is it a triangle? It was another beautiful mathematical problem, S2M30, that we solved. And in the course of generating a proof for this problem in that episode, we showed what? We proved that any point that is interior to an equilateral triangle over here, I already suggestively drew the sides of the triangle, red, green, and blue. And think on your feet, why did Roman, this is me, I'm Roman, why did Roman do this? This is an equilateral triangle with the sides of equal length painted red, green, and blue. So we proved in season 2 episode 28 in the math problem S2M30 that any point shown over here interior to an equilateral triangle has the following two properties. The sum of distances from that point to all three sides of the triangle is what? Is independent with respect to the position of this point. This point can be positioned anywhere inside. I'm not going to delve into the definition of what's interior, what's boundary, what's exterior. For example, in the study of anything that leads to topology, complex analysis, real analysis. We can start with two-dimensional situation, line segments and stuff, or with the three-dimensional situation. There are strict definitions of what's interior, what's a boundary, what's exterior, but here we'll just stay at the intuitive level. Any point that is located inside an equilateral triangle, doesn't really matter where that point is located. The sum of distances from that point to the three sides of the parent triangle is one and the same. That's property number one. Property number two, that sum has a very good, finite, computable, beautiful, and straightforward name, and that quantity is called the height of an equilateral triangle, the height h. So the sum of distances d1 plus d2 plus d3 is a constant for that equilateral triangle, and it is equal to h, the length of any one height. The length of the heights in an equilateral triangle are all the same. So this is in terms of the problem-solving approach that we're studying right now. What will this be called? If the point P over here roams the innards of an equilateral triangle, what is this magnitude called? This magnitude. Exactly, this magnitude is called an invariant, but this time, because we're dealing with geometrically flavored material, what does it say name? How can we qualify what type of an invariant is it? In the previous segments, we covered what? An algebraic invariant. An algebraic invariant, remember? R minus G mod 3. That was the algebra of the underlying problem. But here we're honing in on what? On the geometric invariant, a geometric invariant. Now you guys think on your feet before we roll into the next segment. What is an equivalent of a geometric invariant in this problem with respect to the algebraic invariant that we uncovered in the previous segment? Or you can think the other way. What is the equivalent of the algebraic invariant that we uncovered in the previous segments and in the geometric interpretation of this problem? Put this video on pause, think on your own, and then come back and compare your ideas to ours. A geometric interpretation of our invariant, of our algebraic invariant that we uncovered in the previous segment, shown over here on the upper right side of your screen, is actually quite complicated. We'll get to it in a few minutes. But first we want to start with something that is quite straightforward and we can nail right away. So what is an algebraic equivalent of our geometric invariant? So what is an algebraic invariant that is equivalent to our geometric invariant, which is the sum of distances from any point that is interior to an equilateral triangle to the three sides of the triangle? Well, evidently we saw that the sum of basically the population of our chameleons, or the number of the red plus the number of the green plus the number of the blue chameleons, which remains constant at all times. This is one algebraic invariant, and that is, you see right here, this is the connection that you were expected to make if you were to take on the job of constructing a geometric interpretation of this problem. And that is precisely one of the crux of being creative, exhibiting ingenuity and improvisational skills in mathematics. Many students, when they're told that fact in isolation, they say, oh yeah, I know that, yeah, sure, the sum of distances from any point that is interior to an equilateral triangle to the sides of the triangle is one and the same. It is equal to the height of the triangle. Yeah, sure, I know this theorem. I know how to prove it. But here is the thing. This is the creativity, ingenuity, and improvisation. The ability to connect, to establish the connection between what you know and what is needed. From your web of mathematical knowledge, you should be able to fish out certain facts that you can connect. Seeing the connection between seemingly disparate units of mathematical knowledge is one facet of ingenuity, creativity, and improvisation. So that is what you want to practice. That is what you want to dress rehearse for bigger and better things to come. This is the connection that you were expected to make. Algebra, geometry, geometry, algebra, algebra, geometry, geometry, algebra, forever and ever, interlocked into mutually beneficial relationship. So now that we understand that the algebraic equivalent, the algebraic invariant of that is equivalent to our geometric invariant is the size of the population of the chameleons that lives on this tree. In other words, we say that the height over here is equivalent to the sum r plus g plus b. That is the observation. And from that point on, an absolutely beautiful geometry or geometric interpretation of our chameleons changing colors unfolds as follows. Think about what would you do next now that you know, now that the cat is out of the bag, so to speak. How would you proceed, and what will be the next step in this geometric interpretation of this problem? Given an arbitrary initial distribution of red, green, and blue chameleons as an, let's say, ordered triplet of whole numbers R, G, B. Forget about the specific numbers that we had in this problem, 27, 25, 23, doesn't really matter. Whole positive number ideally, because in this interpretation we work with live objects, let's say red, green, whole number, whole number, whole number, whatever it is. Construct this sum, R plus G plus B is shown over here as, and using nothing but the Euclidean straight edge and compass, construct a line segment that will be a height of the future equilateral triangle within which the whole geometric battle will unfold. Pretend that the triangle that you guys see over here does not exist. All we have right now is a height, which is precisely S units of a length in size. I show over here the lines. You can see I use the number, which is, to some extent, I wanted to pick a purposefully an awkward number. And what is an awkward number in this case? An awkward number in this case is a number that is not divisible by 3. And here, for sample purposes, I use, what is the number over here? I use S is equal to 8. 8 is not divisible by 3. So with nothing but a Euclidean compass and straight edge, in this case, well, how can we do that? Draw a straight line, pick a point on it, and then draw S circles in the consecutive, centered at the consecutive points of where this previous circle intersects this straight line. Stick a needle of the compass over here, open up to 1 unit of distance, circle intersects, that's the point. Stick the needle over here, another circle, another point, stick the needle over here, another circle, another point, and so on. In this case, what's the cost of this algorithm? The cost of this algorithm is precisely 9. One straight line and 1, 2, 3, 4, 5, 6, 7, 8 circles, 1 line segment. This is the future or a future height of the parent equilateral triangle. Done. Now that we have constructed a line segment that will be a height of our future equilateral triangle, we construct the triangle itself. That task is primitive. You guys should be able to do it on your own by my count with nothing but the Euclidean tools of a compass and a straight edge. That can be done in precisely 9 steps. The cost of this construction is 9 steps, and I will highlight this my algorithm. I'll share my algorithm with you guys over here in a loose way. So we have a height. You see, this is the height, and this is some number s units in length. So we stick the needle of a compass, let's say, over here, and we construct one circle of radius s, over here. Then we stick the needle over here, and with the radius s, we construct another circle. It will intersect the parent circle and 2 points, and we repeat the same experiment at this point and at this point through putting the needle of the compass over here, opening up the compass to pass through this point. We construct another circle that will run this way, and we put the needle of the compass over here, open it up to pass through this point, and construct another circle. We'll obtain 1 point over here, 1 point over here. So then we connect, we draw. So this how many? 1, 2, 3, 4. So this is 4 circles. One straight line this way, plus 1. Another straight line this way, plus 1. That's for a total of 6. So these are the straight lines here that will be. And what do you do now? Well, you have the height. This is the height. All you have to do is draw what? A straight line through the point. This one, let's say, call it O. That is what? Perpendicular to the line segment that runs this way. And voila, that's it. This is our equilateral triangle that has given line segment of that height. So this cost with the Euclidean tools is 3. So this is total is 9. So a 9 with an algorithm with the Euclidean cost of 9, we construct the triangle that I showed over here. This is our triangle. And now that we have this triangle, we will construct an absolutely beautiful and actually quite interesting. You guys should think about it on your own without me saying any words. Logically, you will see in a few seconds that this discrete coordinate system will be three-dimensional, but evidently and obviously this logically three-dimensional discrete coordinate system is embedded into what? Into a two-dimensional object, into a plane or in a two space, and we construct this discrete coordinate system as follows. Through s minus 1, or through, in this case, 7 points shown here, 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 and here, and so on, that delineate the unit line segments, s of which make up the length of the height of this equilateral triangle. Using our favorite Euclidean straight edge, we construct s minus 1, or 7 in this case, 1, 2, 3, 4, 5, 6, 7, because we already evidently constructed the side of this triangle as the 8 lines. So we construct s minus 1 straight lines using a Euclidean edge shown over here, for example, this way, 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 and this way. In which manner? Well, each such straight line is either orthogonal perpendicular to the given height. We know how to do that. The cost of each construction is 3, a perpendicular to a straight line through a point on it, 3 Euclidean steps. The algorithm is 3 steps. We construct straight lines perpendicular to S, or in this case, we can say parallel to the base, to the proverbial base, or parallel to the side of the parent equilateral triangle that onto which our height falls. And we use each such of this s minus 1 straight lines will intersect the corresponding side of the triangle at the unique point shown over here. This point, this point, this point, this point, this point, and this point on this side, and this point, this point, and this point, and so on that side. And we will use precisely these points to actually bring our wonderful and awesome coordinate system home by drawing more straight lines that are parallel to the green and to the red sides of the parent equilateral triangle as follows. Through the points, through the points that are located on the sides of the parent equilateral triangle, shown here, 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 and here. Using our favorite straight edge, we again construct more straight lines that are what? That are parallel to, let's say, the opposite side. For example, if we take the green points here, or the points that dwell on the green side of our parent equilateral triangle, in a manner like this, we construct straight lines that are parallel to the opposite side, to the red side of the parent triangle, like so, like so, like so, like so, and like so. And then we grab the points that are located on the red side of the parent equilateral triangle, and using our favorite straight edge, again, we construct straight lines that are parallel to the opposite or to the green side, shown like this: parallel to the green side, parallel to the green side, parallel, 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 and so on. And this way we construct what? We construct a system of smaller triangles, each of which is congruent with respect to each other, and each of which is smaller. In this system of smaller equilateral triangles, partitions, which means tiles, the area of the parent equilateral triangle tight, with no gaps and no overlaps. And technically, in this let's say grid of smaller equilateral triangles, we do not really need the height. You can erase it using your favorite graphing software. You can say click what is it, right click and say show object, or not, or hide object, or whatever. Hide the height. You do not really need it, but for demonstration purposes I will keep it, because the unit of distance, this is one over here, this is one unit of distance. Remember, one, s units of length, or in this case 8. Now the question is, how many such smaller equilateral triangles will there be in our system of triangles? Well, the answer is evidently s squared, obviously, to some extent. Why is that? Well, because we see that the number of, in each logical strip of triangles that runs, let's say, in some sense, vaguely speaking, perpendicular to the height. So this strip, this strip, this strip, or in every, if you will, semi-equatorial belt, if you will, how many smaller triangles will be? An odd number: 1, 3, 5, 7, 9, 11, 13, 15, and so on. So what do we have for the number of triangles? We have 2k minus 1, where k varies from 1 to s. This will be what? 2 times the sum of k, where k varies from 1 to s, minus 1 unit taken s times minus s, and this will be what? S times s plus 1 over 2, so it will be s plus 1 minus s squared plus s minus s is equal to s squared. This is again kindergarten variety computation. We know that we partition the parent equilateral triangle, the length of whose height is s, or the size of the population of our chameleons, into s squared smaller equilateral triangles, as shown over here. Again, I will keep the height visible for you guys as a reminder for what? See, on this absolutely awesome and to some extent weird, logically three-dimensional coordinate, discrete coordinate system, we will measure the distances. How? We will measure the distances strictly perpendicularly to each side, perpendicularly to green side, perpendicularly to the red side, and perpendicularly to the green side. And what is the next step here, guys? What do you think? I will erase this. I will bring in the our favorite RGB notation, the ordered triplet. Then what do you think? Put this video on pause, generate your own idea, come back later on with your idea, compare your idea to ours. But now we see that our order triplet RGB. Again, the algebra of the order triplets RGB over here absolutely beautifully carried into the geometry. Which way? The nodes of our coordinate system will precisely represent each order triplet. RGB, 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 and how do we measure what are the components? The red component, the green component, the blue component of this weird XYZ, seemingly or logically three-dimensional system that is embedded into a two-space. How do we count, or how do we compute? What is the geometry? Well, precisely the geometry. Pick any point and measure the distance which way, orthogonally or perpendicularly to each side. From this point, perpendicularly to the red. From this point, perpendicularly to the blue. From this point, perpendicularly to the green side. And I will show you a demonstration of this idea next. In order to test your understanding of how our discrete, logically three-dimensional but physically two-dimensional discrete coordinate system works, let's try to assign the corresponding components of the coordinates of the points that I marked over here, P, Q, R. Try to do that on your own. Put this video on pause, walk away, do this little exercise on your own, then come back and compare your result to ours. As such, let us start with the point P shown over here. I marked it lightly because I will be erasing this pretty soon, but you guys understand the point shown over here towards the bottom of our coordinate system. Over here it's called P. What is the coordinate of this point in our discrete, logically three-dimensional coordinate system, but weirdly embedded system that is embedded into the two-space, into the plane? And we'll discuss the three-dimensionality aspect of it in a little bit. So the distance of that point, remember, how do we measure distances in our new coordinate system? Perpendicular or orthogonally to each and every side of the parent equilateral triangle. As such, the distance of the point P from the side red, this will be the first component, or the red component of the coordinate will be what? 1, 2, 3. So that is what we write down. 3. Very good. So that coordinate is 3. What is the green component of that coordinate? Well, the green component corresponds to the distance of that point from the green side of that triangle, of the parent equilateral triangle. And how do we measure the distances? Orthogonally with respect to. And this is precisely, you see, this is the height of every triangle, and this is the height of every triangle. This is the unit of distance. 1, 2, 3. So this will be 3 also. This is the green component of this coordinate. And what is the blue component? The blue component for the coordinate of the point P corresponds to the distance of the point P from the blue side of the parent equilateral triangle, which is what? 1, 2. So we'll write down 2, and this is it. Voila. This is the coordinate of our point P on the discrete, logically three-dimensional but physically two-dimensional coordinate system. And we already now know that this coordinate is a geometric interpretation of the algebraic state of affairs, where our happy family of chameleons that lives on a tree bumps into each other, and it undergoes through the color transformations. And at that point, we looked at that family, we see 3 red, 3 green, 2 blue chameleons. That's the point geometrically. Okay, PQ, okay, the coordinates of the next coordinate, let's write it down. The distance from the point Q to the red side is what? 1. So we'll write down 1. Very good. What is the distance from the point Q to the green side? 1, 2, 3. So that will be 3. Very nice. What is the blue component for the coordinate of the point Q? 1, 2, 3, 4. So we'll write down 4. So this is it. There you go. An algebraic state of affairs when in this family at that point of time 1 red, 3 green, and 4 blue chameleons is captured geometrically with the point shown over here on our coordinate system. Again, the assignment, yes, maybe I didn't say it, but when we do the constructions, we do not really color anything. Color is not technically a geometric property. This is something that we infuse our geometric material with. So as a first step, if you want to start doing these things, we color the three sides of the parent equilateral triangle arbitrarily, any which way, it doesn't really matter. I just picked this particular configuration. You guys can pick any other. We color one side red, the other side green, and the other side blue, and that is how we measure the coordinates of our points on this coordinate system. And now let's do the coordinate of the point R shown over here. What are the coordinates of this point? Well, the distance of the point R from the red side of the parent equilateral triangle is what? 1, 2. See, 2 units of distance. 1, 2, 1, 2. Like that. So we write down 2. Very nice. What is the green component of the coordinate of the point? Is 1, because there is only 1 unit of distance. So it's 1, 2, 1. And what is the blue component of the overall coordinate of the point R? 1, 2, 3, 4, 5. 5. This is it. This is that. This is it is that straightforward. 2, 1, 5. This is the point, geometric point, a geometric point that geometrically represents the state of affairs, which is captured algebraically with the ordered triplet of numbers. 2 red, 1 green, 5 blue chameleons in our family at that point. And now the next step. What is the next step? The next step is to understand how to interpret a transition from one colorful state to another. Algebraically, we know how it works. We subtract 2 from any, we subtract 1 from any 2 colors and add 2 to the remaining color. But this algebraic manipulation corresponds to what geometric material? What is the geometric step? Well, we will explain it in the next segment. We know by now that the algebra of each and every color changing mean between any 2 chameleons of distinct colors is captured in the language of ordered triplets. In order to not to show all the possible combinations, I will shy away from the ordered triplet notation, but let us say that in this particular exchange, 2 chameleons of color X and color Y have met. That means what? That algebraically X is taken into X minus 1, Y is taken into Y minus 1, and what? The remaining color Z is taken, the number of chameleons of the remaining color Z is bumped up by 2 because these 2 ones are debited from X and Y and credited to Z, so to speak. So this is the algebra of each and every color transforming mean between any 2 chameleons of our family of distinct colors. What is the geometry of this specific transformation, one transformation? Well, it is quite straightforward. Any such transformation corresponds to a motion perpendicularly. This is the sign for perpendicularly. Perpendicularly away from the Z colored side, perpendicularly away from the Z colored side. Let's say this is the Z colored side. So we move perpendicularly away from that Z colored side by 2 units of distance. See, that's important, 2 units of distance. Not 1, but 2 units of distance. Why 2? Well, because this is over here, we have plus 2. If the algebra of the underlying situation meant plus 17, we would have said, okay, 17 units of length. Or if it were, I don't know, pi units of length, that would have been pi units of length. Here, 2 units of length perpendicularly away from the Z colored side from the point that has the corresponding coordinates X, Y, Z into the point which has the coordinates X minus 1, Y minus 1, Z minus 2. This is the origin, this is destination. You see, in this it is important to understand that we're about to unleash a perfect storm of drawing vectors. In this case, if we draw a vector, then that vector is perpendicular to a given side, it will point away from that side. This is precisely what the plus. See, we increase the number of chameleons of each color, and in our RGB, remember our RGB interpretation, what is the meaning of each component in this coordinate? It's the number of chameleons of that color. In this case, the number of chameleons of blue color is right here, 2. And the number of green chameleons, 1, 2, 3, and the number of the red chameleons, 1, 2, 3 as well. This is the meaning. So if the number of chameleons of the given color is increased by 1, it means that perpendicularly the point is getting closer by 1 to each side correspondingly colored, so the distance decreases, but the distance from the correspondingly colored Z-colored side must increase. So these two distances decrease by 1, this one distance increases by 2, perpendicularly away from the Z-colored side. And if that theoretical material or theoretical rule is not very clear, then here is a demonstration for those who is not really sure how that works. We will do it in the next segment. In order to test our understanding of how geometrically an algebraic transition from one color distribution to another in our happy family of chameleons work, let us consider this algebraic transformation. Let's say at this moment of time there were 2 red, 3 green, and 3 blue chameleons, and 1 green and 1 blue chameleon bump into each other, and already we know algebraically this transition corresponds to what? 3 green minus 1 green becomes 2 green, 3 blue minus 1 blue becomes 2 blue, and these two guys are credited to the happy team, red team. There are now 2 plus 2 is 4 red chameleons in this family. Again, we know that the sum total of RGB 3 and 3, 6, 8, and over here 2 and 2, 4, 4 and 4, 8 is an invariant. And now, how do we capture this one legal color changing transformation geometrically? Well, we go back to the previously studied material. We find the geometric representation of this algebraic state of affairs. This point is over here. You guys tell me why. We also have this number, but we keep it for now. For now, we keep it in our back pocket. This will be used for double check. So now we said what? Because this is the transition. So what is X and what is Y from the previous segment? X, Y, Z. Z colored is Z is red. Let's say X is green, Y is blue. So the distances to the green and to the blue colored sides of the parent triangle geometrically did what? They decreased by 1. So the point, our geometric point that captures the algebraic state of affairs, moved closer to the green and the blue sides, and it moved away from the red side by what? By 2 units, but it did not move in any haphazard way. Orthogonally away from, or perpendicularly away from. Perpendicularly, it means this way. So this will be the perpendicular distance. So this will be our representation. This will be our motion over our coordinate system. This 2, let's call it 2 vector. We understand what does 2 vector mean. 2 vector means that this vector is 2 units of length. 2 units of length. 1, 2 units of length. This is a geometric interpretation of this algebraic transition from one to another. As a double check again, pull this guy, yank this guy out of your back pocket, and now let's do some kindergarten level arithmetic, which all comes down back to, again, my remark that a beautiful mathematical idea, a successful mathematical idea, is indistinguishable from a beautiful work of art. A sculpture or a painting, the painting that you saw a couple segments ago, it belongs to the brush of a great master called Sargent. His last name was Sargent. Every detail is in the right place. Every following step is easy. It follows, it rolls off the mathematical tongue, so to speak. Everything beautifully and coherently comes comes together in a beautiful way. So here, what is the distance of this point from the red side? 1, 2, 3, 4. 4 units of distance. That means that what? This geometry of this point means 4 is the number of chameleons of which color? Red color. And here it is, 4 red chameleons. What is the distance of this point to the green side? 1, 2. 2 units of distance. And that corresponds to the number of chameleons of color green. Wonderful. And what is the distance of this point from the blue side? 1, 2, 2. And what is 2? Geometrically, or a geometric distance here corresponds to what? The algebraic number of chameleons of that color, blue. So everything is absolutely wonderful. And if you measure the distances from this point to the green and to the blue sides, in this point and in this point with respect to this one got what? It got closer to the green and the blue sides, and it got further away from the red side. And this is precisely what happens. And now, guys, again, think on your feet. You can see where this arrow points. What is this point right here? The vertex, one of the vertices of the parent equilateral triangle, and the other vertices, the vertex over here and the vertex over here. Actually, I should, as a hint, guys, for you, I should draw it in the corresponding color. This will be a blue point, and this will be a green point right here. This will be a green point. What do these vertices of the parent equilateral triangle represent? By now, it should be evident to every member of our audience that geometrically, this here red vertex of the parent equilateral triangle that sits directly opposite the red colored side of that triangle represents what? It represents algebraically, actually, a solved state of the problem. Why is that? Well, this red point is as far away from the red colored side as possible in our weird, strange, but beautiful coordinate system. And what is the distance of that point from the green and the blue sides? 0. So algebraically, this point will have which coordinates? It will have coordinates 8, you see, 8, and then let's say 0. I use red and blue for 0 again. You see, this is one possible state. In other words, it so happened that through the legal and valid color transformations across the members of the family of chameleons, all chameleons became what? They all became red. No more green, no more blue. All chameleons are red. So we've got to this point. Now, this vertex over here will be called blue. In the previous segment, I gave you guys a hint. It's blue because it's opposite to the blue side. What is the geometric interpretation of that point? It's the point that is farthest away from the blue side. And what is the distance of the point from the green and the red side? 0. It means that all the chameleons in this happy family became what? All 8 chameleons, or S in general, this will be S, R plus G plus B. All the chameleons in this happy family became blue. They became blue, and consequently, this is the green point. It is furthest away from the green colored side of the parent equilateral triangle. The distance of that point to the red and the blue side is what? 0. The maximal distance to the green side is what? S, R plus G plus B, or 8 in this case. So how would we render the coordinate of this system? It will be 8 for the green, and it will be 0 for the red, and 0 for the blue. And now you guys understand what is going on. So now, once we realize that, the next step, remember the beauty of the painting, the beauty of the idea in mathematics. The ideas roll off your tongue, and now you see what's going on. Aha, so now a geometric interpretation of actually not only being able to solve the problem, but any legal transition from the, let's say, triplet RGB to a triplet R prime, G prime, B prime, geometrically corresponds to what? Geometrically, this transition where 1 is subtracted from any two numbers and 2 is added to the remaining 1 corresponds to what? To a possible orbit that is constructed from these two vectors from any point through legal two jumps away from the correspondingly colored sides of the parent equilateral triangle, if that orbit exists from one point to another, only through the legal orbit, through the legal two jumps or two steps. So now let us do just that. Let us try to construct. Let's see what happens if we start, for example, again, when I recommend that you guys do it on your own. Do not be lazy. You will learn a lot. You can do it by starting with any point. Let's say we started with this point. So from here, evidently, two jumps, and we got to this point. And then what other transition is possible? What is the legal transition here? Well, another two vector over here into this direction over here. So this is the red point, and then into the red point over here. So if we had this distribution, algebraic distribution of chameleons, that many red, that many green, that many blue, then we go jump, 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 problem solved. All the chameleons are red, problem solved. The interesting question now becomes is the following: is this the only orbit? Is this the only orbit that is possible from that node? What other possible legal jumps are possible in this case? What else can happen? Well, let's see. We can jump from this point over here. You see, from this point, we can jump over here. Now, I will use the red color because ideally you want to use a different color, but I don't have that many different colors for the chalk. But you guys should use a different color, for example, orange, pink, and some other purple, for example. But here, what other valid jumps that are perpendicularly away from all the other possible different colored sides in the triangle are possible? Let's construct this network of two vectors that are possible. Let's do this. So what else can we do? Remember that if we draw, the rule here is the following from the previous segment. If we draw a vector, that vector must be pointing away from a certain colored side, and it must be perpendicular to it. So from this point, what other two vectors can we draw that are perpendicular to what? To the blue side, evidently, and the green side. So we can point perpendicularly away from the blue side over here. We can jump over here. And we can also point over here. We can point over here. Why is that? Because this will be perpendicular to the green one. We can also jump over here. So this will be another point. We'll color it red. This is it. We cannot step out of the boundary. Our universe, so to speak, ends over here. What else can we do here? Well, we can jump perpendicularly to the green side this way. This will be another point. And from this point, what can we do? We can jump this way. We can jump this way into this red point. You see it's perpendicular and 2. From this point, what can we do? Well, we can jump back over here because this is perpendicularly away from the green side. This is a legal jump, perfectly normal. What else can be done from here? Well, from this point, we can jump perpendicularly to the red side over here. We can jump into this point right here. This guy, we can jump also over here. See, this vector is not perpendicular to green, but that's fine because that vector is perpendicular to the red side. It comes under an angle with respect to the green side, that's fine, but it is perpendicular to the red colored side. Okay, from this point we can do this. We can jump over here. From this point we can jump over here. What else can we do? We can jump away from the blue side over here in this direction, you see, in this direction, perpendicularly with respect to the blue side. So every time we're now already getting the hang of it. If we have some network of arrows, these arrows always traverse circle in the same direction. So they go here, here, and here. In this direction, they go this way, and this way. So in a way, we construct a network of slightly larger equilateral triangles whose sides are what? Whose sides are 2 units in length, 2 equilateral triangles. And in that fashion, we work further. From this point, we can get over here, right? Perpendicular to the green side. From here, we can get away from the blue side. We can jump over here. So this is our point. What else can we do? Well, we can jump another 2 units of length over here into this point, and then into this point right here, into this point, away from the blue side perpendicularly this way, you see, this way, and these 2 units over here from this red point to this red point right here, and perpendicularly still away to over here. We can jump to over here. This is it. What else can we do? What other possible motions that are perpendicularly away from some side? We can jump from here perpendicular to the green side away from it into this point right here. And from this point we bounce where? We bounce perpendicularly 2 units all the way up right here. This way. And what else? Evidently perpendicular to the red side, we can jump this way. This is the vector, and this way. You see? These are the vectors. Now let's see if we missed anything. So on this level we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and our 15th point. So it looks like I have covered all the points that are reachable if we want to get to the red vertex of the parent triangle. For example, we see that the orbits are not unique. Let's say we are given an algebraic state of affairs that corresponds to this point. How can we transform this family of chameleons to be all red in color? Well, let's see. We can go, for example, this way, and then boom, home run. Or we can go from here to here. We can go here, this way, and then this way. This is actually quite beautiful once you take your time to understand what is going on. Again, keep me honest, guys. Maybe I'll take a short break to verify that I have captured all the arrows. If I missed anything, actually, yes, I did. I missed this one. Look at this. Perpendicular to the blue side, we can go this way. We can come up this way. So all our triplets should be connected. So by now it looks like, did I nail all of them? No. So this one here is another one. Yes, perpendicular away from the green side. We can this is an arrow here. What else? Did I miss anything else? Yes, I did. We can go this way. Look at this. Perpendicular away from the red side by 2 units of length over here. This is our beautiful network of vectors of length 2. This is how these things work. So now we understand that from any red node of our discrete coordinate system, we can get to the red vertex. In other words, we can make the entire family to be red in color. We can solve this problem. But think about this. We cannot, from no red point shown over here, we can get to the blue point or to the green point. In other words, if we start with an algebraic state of affairs that corresponds to any red point in our coordinate system, we can make our family all red in color, but we cannot make the family all blue or all green. And again, another short quiz for you guys. Compute what is the residue. Let's say I will use R minus G mod 3 is equal to what? Give me the number for any red vertex. And by now you understand that why did that happen. There is a little bit our drawing is a little bit not symmetric. I did it on purpose because I picked this awkward number 8, because 8 is not divisible by 3. Think about what will happen if our sum is divisible by 3. It means that this number will be divisible by 3. Evidently, we will be able to get to that state from any node, but not in the case when the number is not divisible by 8. And our network of, in this case, red vectors is slightly skewed. It's a little bit off. It's missing something to be completely symmetric, but nonetheless, it's still beautiful. Again, one more time, we all understand that geometrically a solution of the problem now becomes what? It becomes a very straightforward task of finding a trajectory from a point that represents the algebraic state of affairs to a reachable vertex of the parent equilateral triangle by following the arrows that represent the legal moves that are possible for that particular, for the value of this invariant. I'll show it in the next segment. You guys think on your own, put the video on pause, walk away, and then compare your ideas to ours. Now that we'll all understand how a network of two vectors is constructed over strange and weird but awesomely beautiful coordinate system work, we basically bring it home, and precisely because I picked an awkward number, 8 is not divisible by 3, there's interesting scenarios develop. We finish this partitioning of our nodes of our triangle lattice all the way through. I will not hold you guys with me to witness me do all of this, but you understand. Let's say we do green one. The distance from the green one, this is our green vertex. How can we get to the green vertex? Well, we can get to the green vertex from this point over here, you see? Why is that? Because from this point, this will be a green point, we can jump 2 units of length with our vector right here, perpendicularly away from the green side, evidently. So also we can jump to the same point this way, perpendicularly away from another point over here. This will be a green point, another green point over here, and this, from this green point we can jump over here. And is this the only possible legal orbit from any possible node of our triangle lattice to the green vertex? Evidently not. For example, what can we do over here? In this particular case, from this point, we can jump what? We can jump away from the blue side, for example, this way, into this point, right here, to this point. And from this point, this will be our green vector. And then to this point over here, this is another green point. This is our green vector, points away, perpendicularly away from the blue side. Here we point away from the green side, perpendicular into this point right here. This is another green point, and perpendicularly away from the red side over here. You see, we have another beautiful cycle. Bam, 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 green point, green point, green point, and so on. In like manner, we complete this partitioning of the nodes of our triangular lattice using the green color. Every time we hit the legal point, we color it red, basically. So we go from here to here. Which way we can go here? And as a final step, we partition the nodes of our triangular lattice into the blue colored ones, or the ones from which the blue vertex of our parent equilateral triangle is possible. And in the previous segment, I misspoke. I'm sorry. I apologize to you guys. I meant to say every time we reach a legal node of our lattice that is colored in green, we color it green. Evidently, I said red, but it's evidently green. So now we have the certain number. I'll discuss that number, but you guys can already figure out this is basically triangular numbers that are happening in when it comes to counting the number of nodes in our coordinate system. So right now we colored all our nodes, reachable nodes, as red and green. Before I ask you to compute the value of the invariant for all the red nodes, and that number is 2, red minus green modulo 3 is 2. For the green colored nodes, that residue or that invariant is 1. Evidently, for the blue ones, it will be 0. And the way you do it, it doesn't really matter. Pick any good number. For example, the number in the middle over here, 0 for red, 4 for green. Evidently, 0 minus 4 is -4. -4 plus 3, -1. -1 plus 3 is 2. Bam. This is your Bob's your uncle. 2 is the invariant. You do the same thing for the green points and for the blue points, and that is what you have, the residues of 0, 2, 1, and 0. These are all the possible values for the residues upon integer division by 3. So we already feel that some sort of equivalence relation or equivalence classes are happening, and indeed, once we complete our partitioning and coloring the nodes, we will see that this will be the case precisely because here the number 8 is not divisible by 3. So what do we do here? Well, this is our blue node. So how do we get to this blue node? This is the point right here, blue node right here. So we do a 2 vector into it here, then another jump over here. This is another 2. This point will be blue. This will be a vector into this point over here. And again, you already see what? Green, red, blue, green, red. So all the points are painted already in blue color, and in like fashion we keep moving. We paint this point blue, this point is blue, we come here, and then to jump from here, this point is blue again, we jump over here, and again with respect to every point we start jumping away from. For example, from this point we can jump away from the red side. Which way? To jump over here, one jump that is 2 units in length. Blue point away from the green side into here, into this point right here. This is another 2 green 2 vector right here, and we keep going this way, and we can jump this way, and so on. We complete the coloring of the nodes of our lattice with the color blue. When you will be working with your favorite graphing software, I recommend that you select all the vectors that you constructed, all the red, all the green, and all the blue vectors that you constructed during the previous steps, and make them invisible. For example, I use the free software called GeoGebra, and in GeoGebra I can simply click on all the vectors, right click on them, and then check off the checkbox that says show object, and that makes all the vectors disappear. Once you make all the vectors that you constructed in the previous steps invisible, you will clearly see that all the nodes of our weird and strange but beautiful triangular discrete coordinate system are partitioned actually into 3 distinct equivalence classes, precisely because in this case the total size of the population of this family of chameleons, S, or the sum of the red plus the number of the red plus the number of the green plus the number of the blue chameleons, is not divisible by 3. Now it is a straightforward matter to answer the following question. Okay, how many such nodes in our triangle system there will be? The reason it is more than straightforward to answer that question is because these nodes pretty much are the embodiment of a popular definition of triangle numbers. If S is the height of our parent or generating equilateral triangle, then how many rows of such points we will have? S plus 1. Consequently, TS plus 1 will be the number of nodes in our triangular system, and that we remember is s plus 1 times s plus 2 over 2. In our case, for the sample demonstration, I picked number 8. So the number of nodes in my demonstration coordinate system will be what? T8 plus 1, T9. T9 is what? 9 times 10 over 2 is equal to 45. And 45, amazingly enough, is divisible by 3. That is why we can partition all 45 nodes of our triangular lattice into 3 distinct equivalence classes. Which way? There are 15 red nodes shown here, 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 and here. These are the first nodes that we constructed with you guys. There will be 15 green nodes, green points, and there will be 15 blue points. 15 blue points. Now, if you are new to equivalence relations and equivalence classes, then do not worry about it too much. It is not that complicated, but it's very important to eventually get a grasp on this thing. And in a lightning round, this equivalence business means the following. Technically, yes. Let's say we take these two red points, for example, this point and this point, you see? At the immediate technical level, these two mathematical objects are distinct. Visually, this point is not this point, and this point is not that point. Algebraically, we know that these 2 points are described by 2 distinct triplets, ordered triplets of whole numbers. So that is the fact. Yes, they are distinct and they're different. However, from the equivalence relations perspective, if we're willing to ignore this immediate, the fact that immediately they are distinct, and look at these 2 objects, 2 distinct objects, from a bigger perspective, then we can say that these 2 points are equivalent. Why? Because it is possible to get from this point to this point, and it is possible to get from this point to this point via a set of legal 2-vector jumps. But for example, this red point and this green point are not equivalent. They are also distinct at the technical immediate level. These 2 objects are distinct, but they're not equivalent because it is not possible to get from this red point to the green point, and it is impossible to get from this green point to the red point through any series of legal jumps. In other words, there does not exist an orbit that takes us from this red point to the green point, and conversely, there does not exist an orbit, a trajectory, or a directed path from this green point to this red point. And that is pretty much everything that for now we need to know about these equivalence classes. Technically, that means that every node in our triangular lattice belongs to precisely one class, and no 2 classes have even one element in common. In a jargonish way, they said that these equivalence classes do not intersect. So what kind of statements can we make, useful and interesting, mathematically deep statements can we make? Well, the first statement that we can make is the following. If we pick any one node that belongs to one and the same equivalence class, such as, for example, this red point, from that red point, it is possible to get to any other point that belongs to the same equivalence class. In other words, from this red point, it is possible to get to any other red point in our coordinate system. There exists a legal orbit from that point to any other, pick any other point, and by tracing the corresponding arrows, we can get from any point to any point. Sometimes such an orbit is unique. For example, there is only one way to get from this point to this point. This is evident by this vector. And from this point, we can get to this point evidently, only in one way, left and right. However, and in general, such orbits are not unique. For example, from this red point, in how many distinct ways can we get to this point? Well, we can go from this point left, right, left, right, and we can go left, right, right, left at the minimum. And by the looks of it, from this point, if we get to this point, for example, instead of coming here, we can jump this way, this way, this way, and this way. So there are many ways to get from this point to this point. It's one statement. And the same statement applies to all the other ones. This is the case from any blue point, it is possible to get to any other blue point, and from any green point, it is possible to get to any other green point. The, in some sense, algebraic fact that no two equivalence classes intersect geometrically here, it is very descriptive, very visual. It can be seen what? It can be seen that there is no legal orbit from a node of one color to a node of any other color. So that means that from no red point can we get to a green point, and from no red point, green point, and from no red point we can get to any blue point. And likewise for the other colors too. From any blue point like this one, there is no way to legally orbit into a green point or into a red point, and so on. That's number one. Number two, again, all these statements revolve around the fact that the size S of the population of chameleons is not divisible by 3. From any node of our coordinate system that we constructed, it is possible to get to one and only one vertex of the parent or generating equilateral triangle. We showed this with the construction. And what does that mean? That means that in this case, for example, from any red point, it is possible to get to the red vertex of the parent equilateral triangle, which means that this family of chameleons can be painted all red, provided we start with a red point. In other words, if in general the value of the invariant r minus g mod 3 is 2, at any point that has this, the value of this invariant attached to it, can lead to all chameleons in this family being painted red. Likewise, if we pick, we start with any point to which they're attached the value of the invariant r minus g modulo 3 is 1 in our case, that means that the entire family of chameleons can be painted green, And how do we do that? Again, given that point, we hop on that point and we just plow an orbit by following the green arrows. Basically, that's essentially what it is. Lastly, any point which has the value of the invariant r minus g mod 3 equals 0 attached to it can be taken into the corresponding blue vertex shown over here, which means that all the members of this chameleon family can be painted blue. But in this case, again, what do we see? When S, the total size of the population of the chameleons, r plus g plus b, is not divisible by 3, the entire family can be painted in one and only one color. Only red, or only blue, or only green, depending again on what is the starting point of our journey, depending on which basically order triplet of whole numbers algebraically is attached to that point. So that much we understand. So this covers the general case when S is not equal to, S is not divisible by 3. We know which color is achievable depending on the starting value of the corresponding triplet, and we know how to get to that state by plowing an orbit and following the correspondingly colored arrows. Now let us think about the case when the, let's see, case when, that was the case when S mod 3 is not 0. Now let's look at the case when the sum, or the sum S mod 3 is 0, when the total number of chameleons is divisible by 3. Let's think about this together. I already said something about this in the previous segments, but let us go over it one more time. That means that if it is possible to paint all the chameleons in this family one specific color, the number over here will be S, will be what? Divisible by 3, divisible by 3, divisible by 3. And what does that mean? That means that unlike the case when the population of the chameleons was not divisible by 3, and that family can be painted one color. In the case when the population is divisible by 3, that family of chameleons can be painted any color. It can be painted all red, or it can be painted, and it can be painted all blue, and it can be painted all green, but only in which case? Well, we know the invariant is reachable, like when in the blue case, the invariant was 0, and this will be the case for all the other 2 vertices when the population is divisible by 3, right? That means that that family of chameleons can be painted any one of these 3 colors, red, green, and blue, only in which case? If the starting point in our coordinate system has the value, which value of the invariant attached to it? Precisely, if the point has the value of 0 for the invariant, r minus g mod 3 attached to it. For example, I on purpose picked the number 8 for demonstration purposes. That is not divisible by 3. But for you guys, I recommend, for example, change 8 to 9, construct the coordinate system that is based on the height 9, and then see what happens. And in this case, you will see that there will be only one class of coordinates, one class of points, from which it will be possible to reach all 3 vertices of the parent or generating equilateral triangle, and we know that that state corresponds to the requested state. All the chameleons in this family I painted color blah. So this is possible. When this is the case, all the colors are reachable as long as we start from a point that has the value of the invariant r minus g mod 3 attached to it equal to 0. And now this analysis covers all the possible cases. We know when it is possible to reach the requested state and how it is possible to reach. The mechanics of how can actually be quite visual. All we have to do is find the point and then have loads of fun tracing the correspondingly colored arrows. And if we care, we can then record our orbit from here to there, and then basically trace these points, throw these points into the correspondence with the triplets, and write down an algorithm that takes the family from this initial state to the requested state, bam, 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 write down the sequence of triplets, and present our solution. And now in the next segment, we will answer the question, which is slightly more general. When it is possible to take a given order triplet of numbers RGB and following the rules stated in the at the beginning of this episode, put that triplet into the state where the numbers are R prime, G prime, and B prime. Before I answer the question, more general question, when it is possible to take one order triplet into another using the rules described in this problem, I think I would like to mention that in the previous segment, I forgot to tell you guys that when the population of chameleons is divisible by 3, such as, for example, 9, and I encourage you to experiment with 9, I forgot to tell you that precisely because the invariant equal to 0 will be attached to all 3 vertices. Technically, it will not be the case that all the vertices in this triangle lattice will be strictly partitioned into equivalence classes. Fundamentally, yes, at the big scope, they will be all different, but once you play with numbers, for example, for 9, you will see 55 will be the total number of nodes will be 55, and 55 is evidently not divisible by 3. It is not too difficult to see what is going on. Try to think about it on your own. In any case, we now know how to answer through this weird and strange but beautiful coordinate system through a geometric interpretation of this problem, and I'll say a few words at the end of this segment for the curious souls. We now know we can answer a more general question. Given an ordered triplet of numbers RGB, again, my order is irrelevant, I just picked it for definitiveness, Yeah, it is possible to take that ordered triplet into an ordered triplet. Obviously, we keep the positions in the destination triplet of the color assignments the same. If sits in the first spot, then red should sit on the first spot. If green is in the middle, then green should be in the middle. If blue is on the right, in the original triplet, it should be on the right in the destination triplet, of course. So this transition from one order triplet to another, according to the rules, subtract 1 from any two numbers and add 2 to the remaining one. That transition is possible when at least two numbers in this triplet, in the original triplet, are positive. Think about on your own why. They should not be negative. If at least two numbers are positive and these two conditions hold. The sum is the invariant. The r plus g plus b is equal to r prime plus g prime plus b prime. That is the first condition. And the second condition is the value of the invariant r minus g modulo 3 for the first triplet is exactly the same as the value of the invariant r prime minus g prime modulo 3. The values of these invariants must agree, and then the transition is possible, and we presented an algorithm of how to do it visually or geometrically, depending on whether the sum over here is divisible by 3 or not, and that solves this problem in general. And here a few words about, for the curious souls, a few words about why I kept mentioning the fact that we have a strange and weird coordinate system that is logically three-dimensional, but evidently it is embedded into the two-dimensional structure, the plane. Those who are not interested can skip forward and go to the next challenge, but for the curious souls, now go back to the basics of theoretical physics. And does anyone know what is a degree of freedom in theoretical physics is? Think on your own. So a degree of freedom in theoretical physics is a parameter that is attached to an independent parameter, or a notion that is attached to an independent parameter, the smallest number of which completely describes the time evolution of a given system. For example, if a particular, let's say, material point can only traverse a straight line, then technically it can be here, it can be here, or it can be here. We need only one parameter. This is also connected to the so-called generalized coordinates to completely describe the motion of the point. So that system has 1 degree of freedom. If a point can roam the plane in any two independent directions, again, we need two independent numbers, 2 degrees of freedom in that system. If a point can traverse can get to any point in 3 space, then it is said that that system or that point has 3 degrees of freedom, and so on. In our case, again, we know that on the one hand, because the whole caboodle can be embedded into the Euclidean, let's say, plane, or maybe it is interesting to see what will happen here. Can we gain more mathematical insight if we embed all this thing into the complex plane, for example? Why not? That's an investigation. So evidently we can embed the whole thing into the, let's say, Euclidean plane. We need 2 independent numbers. They offset from, let's say, proverbial x, they offset along the proverbial y, 2 numbers, 2 degrees of freedom. This is a plane, nothing controversial. However, the reason I say that this is our, let's say, point that orbits a specifically colored path of vectors has 3 degrees of freedom logically. Why is that? Well, because it can execute the motion in 3 seemingly independent directions. In other words, our point can move perpendicularly to the red colored side of the parent or generating equilateral triangle. Our point can move perpendicularly to the green colored side of the parent or generating equilateral triangle, and our point can move perpendicularly to the blue colored side of the parent or the generating equilateral triangle. And that's geometrically, that's independent motions in 3 seemingly 3 independent directions. And this is also confirmed by what? We need a triplet. We need three. One, two, three. We need three numbers. You see, we need three independent, seemingly independent numbers to describe, to lock in a unique position of the point. Of course, this, in some sense, maybe if you want to call it contradiction, then maybe this contradiction is resolved due to the fact that, of course, we have a certain connection between the numbers. The way these numbers evolve, they're not completely independent, of course. We do have a constraint, and that is the situation that resolves a seeming contradiction. How come we have a three-dimensional something in a two-dimensional something? It seems to be absurd, but it is really mathematically not that absurd. Three numbers, but the evolution of these numbers is not independent. We have a strict rule: -1 from any two, +2 to the remaining one, and that is still a beautiful situation. And again, you remember season 1, episode 2. I don't want to sound like a helicopter parent, but do the right thing, practice mathematics correctly. Watch season 1, episode 2. We describe how to do things. When you solve a problem, you step back, you inhale all the experience, squeeze it into one or two short sentences that captures the essence of what just transpired, and then try to abstract and generalize. How will you abstract? Well, invariant is what solves the problem. This is your abstraction. What's generalization? Well, we feel that the any interior point in the equilateral triangle has which property? We already discussed, right? The sum of distances to all three sides is independent of its position. It's an invariant. If we try to generalize, we step up from two space into three space. What is the next best thing? Well, instead of equilateral triangle, we take what? We take a regular tetrahedron. And in the regular tetrahedron, is it the case that somehow the sum of distances of any interior points to any four, our regular tetrahedron has how many? 1, 2, 3, 4. 4 sides, 4 planes. So if we pick any point inside the tetrahedron, will it be the case that the sum of distances from that point to all 4 sides is some sort of invariant? True, false, maybe, but that's an investigation. If it is the case, maybe we can construct some other strange but beautiful coordinate system inside the tetrahedron, and so on. Now, this is it for the mathematical problem S2M51, and we will move on to a new challenge next. Some of the viewers of our channel are asking me, Roman, in the title of your channel, you declare that you will be doing mathematics, theoretical physics, and computer science. So far, we see a lot of mathematics, but where is the theoretical physics? Where is the computer science? This is a valid, perfectly valid question, but a valid response to that valid question is the following. Any properly structured program that means either theoretical physicists or computer scientists should have a mathematical, the corresponding mathematical curriculum running ahead of these two majors by evidently at least one semester, but ideally one semester is nothing. In the best scenario, the mathematical curriculum should run at least 4 semesters or 2 academic years ahead of the program in the computer science or theoretical physics, perhaps even more so in theoretical physics, because both of these disciplines, theoretical physics and computer science, are highly specialized applied mathematics. Theoretical physics is applied mathematics in this specific flavor, and computer science is fundamentally and essentially applied mathematics, but in this specific flavor. As such, before we can do either theoretical physics or computer science the way it should be done, we should know and learn a lot of mathematics prior for a successful study of this or that subject. So in this case, anyway, we're taking a short break from the dedicated and planned study of the problem-solving approaches. In a way, to give you guys a heads up, this episode concludes our dedicated study of the invariant problem-solving approach. And so far, I have only one more problem-solving approach in mind that we will study in the dedicated fashion. That is, I refer to it as mathematical equivalence. This is pretty heavy problem-solving approach. All the other ones do not really require too much specialized knowledge, and using nothing but situational awareness, you can study them successfully. For mathematical equivalence, you need some amount of mathematical maturity. It wears better the more mathematics you know, and I'll cover the mathematical equivalence problem-solving approach in the next few episodes. But for now, we'll take a break for 2 episodes. In the next episode, we will do a computer science program. Don't forget to keep the numbering correctly. Season blah M something is the problem in mathematics. Season blah P something is a problem in physics, and season blah CS is the problem this and that in computer science. So far in season 2, we only officially did 1 computer science problem, so this will be the computer science problem number 2. Pay attention to this fact that this will be C2 S2 CS2. The numbering of computer science and physics problems is independent. They're all independent from each other. And in the following episode, we will do 1 problem in physics just to throw some physics into our curriculum. So in the computer science problem S2CS2, we are asked to find all the whole non-negative pairs of numbers A and B using nothing but the integer arithmetic. This is important over here. No mathematical libraries of any kind, only the standard operation of, let's say, multiplication. I don't want to give out too much, but this is an important restriction, that using nothing but integer arithmetic only. Find all the pairs A, B of whole non-negative numbers such that the sum of squares of these numbers is less than a whole positive number that is fixed, and it is given ahead of time. Let me probably write it down here. The number n is fixed. N is fixed ahead of time. So on the input, your algorithm will be given this 7,359. Boom, ready, set, go. Now, the thing is this, like I said, this will be deviation from our standard traditional curriculum of studying a dedicated problem-solving approach. Here, solve this problem any which way you can. I'm not gonna tell you how to solve this problem. Find your own way. And there is a problem-solving approach that unlocks a very elegant solution of this problem. We studied this approach. I'm not gonna say which one. Have fun figuring this out on your own, and evidently those of our viewers who are not shy with a keyboard, they already see that the big O of n square is an algorithm that takes exactly 0 intellectual effort, has 0 intellectual voltage, straightforward. This is a knee-jerk reaction. Boom, 5 seconds and we are done. This is not what we want. We do not want that. What we want is, we want big O of square root of n. That is the challenge for you guys to figure out how that can be done. So again, one more time, using nothing but integer arithmetic, print all the pairs of numbers A and B, each of which is a whole non-negative number, such that the sum of squares of these numbers, A squared plus B squared, is strictly less than a fixed whole positive number that is given ahead of time using the big O notation. The time complexity of this algorithm should be square root of n. This is it. Good luck. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will share my solution of the problem S2CS2.